we present RoboCAP, robotic classification and precision pouring of diverse liquids in granular media with capacitive sensing. Current approaches for robotic classification and manipulation of various substances include spectral reading, haptic feedback, vision, audition, or some combination of the above. These techniques often present with limitations on container and substance varieties, interference from other sources, or require multimodal approaches. In this paper, we introduce RoboCAP, a robotic end effector with embedded capacitive sensing arrays in its fingertips to allow for classification and precision pouring. Our contributions include designing a robotic end effector with integrated capacitive sensing electrodes, using this end effector to infer materials of household containers and substances, and introducing a model-based controller that enables precision pouring of substances from containers that can accurately pour diverse granular and liquid media. We designed a multi-electrode capacitive sensing system integrated within the parallel jaw gripper of a U-Factory X-Arm7 robotic manipulator. Our RoboCAP system measures the self-capacitance of the container and substance directly in the vicinity of each electrode. For classification, we used 9 unique containers and 9 unique substances to produce a total of 81 unique combinations of container and substance. To collect data, we placed each container in the RoboCAP gripper. Different container-substance combinations produce different capacitance values. The normalized capacitance values on the graphs increase as the gripper closes around the container. In this example, we use lentils in a polypropylene or PP plastic container and oil in a wood container. After this preliminary step of data collection, we partition our data into windows corresponding to a single RoboCAP gripper closing action. The measured capacitance values are used to calculate the first-order gradient using finite differencing, which is appended to the original values. We standardize the data to zero mean and unit standard deviation, fit on the training data, and applied to the testing data. Finally, we train a random forest classifier using the training data. This is our RoboCAP classifier. The RoboCAP classifier provides us with an overall accuracy on the testing data. Each predicted label consists of the container and substance predicted, from which we calculate the accuracy just for the containers and just for the substance. Our overall accuracy is 84.7%. Our container accuracy is 97.8%, and our substance accuracy is 84.9%. Our strategy for robotic pouring consists of 2 parts. First, to determine when to stop pouring, we use an over-pouring weight estimation function, or OWE, to fit the relationship between the target weight and stopping weight. The second part is the pouring control process. We use a poured weight estimation model, or PWP, to predict the amount of a substance poured and reason about when to stop pouring according to the inputted capacitance values from the RoboCAP gripper. Our RoboCAP model training process begins with the data collection for our weight estimation model. After collecting our training data set, we use this data to train our PWP model. Next, we leverage this PWP model to assist in the data collection for fitting the OWE function. The difference between the weight that the PWP model predicts it poured out and the ground truth weight is the overpouring weight for fitting the OWE function. Then, we use a simple second-order polynomial to fit the relationship between those 2 weights to be the RoboCAP model. This demonstration shows how we collect training and testing data for each substance, along with the collected real-time capacitance changes and weight changes. For the test trial, we also show the weight predictions. Our approach has strong performance with an overall mean error of 3.2 grams among 5 substances. Compared to the commonly used methodology, behavior cloning, our model is superior in any substance or any target weight. In conclusion, we designed a robotic end effector using capacitive sensing electrodes. We used the capacitance reading from these integrated end effectors to train a classification algorithm that infers the materials of household containers and substances. Finally, we introduced a model-based controller that enables precision pouring of substances from containers that can accurately reason over diverse media poured.